Okay, I think we're live. Okay, cool. What's up, everyone? Uh, hope everything's doing well. This video should be quite short, but in the case it isn't, I do talk a little bit slow, so please feel free to speed up the video. I always do this. Please feel free to speed up the video to your liking. Yeah, and just scrub through it with any part you need to look at. Today we're going to be going over a cycle 5 test or cycle 5 quiz. Yeah, and yeah, let's get into it. So get that out of the way. Number one, right? Number one right here is so if you apply the same amount of heat to a 5 gram block of aluminum with a specific heat of 0.9 and a 5 gram block of iron with the specific heat of 0.46, the block of iron will experience a greater increase in temperature. So looking at this problem, right? The aluminum has 5 grams, and then the block of iron. Uh-oh. Yeah, so the block of iron has 5 grams, and then the block of aluminum also has 5 grams. And so what this means is that the mass are constant. So the thing we need to be looking at are the specific heats, or the 0.9 and then the 0.46. So what it's saying is that if we apply the same amount of heat to it, that's both constant, the block of iron will experience a greater increase in temperature. And look, right, the block of iron has a specific heat of 0.46, and then the aluminum has a specific heat of 0.9. And what the specific heat means is that the higher the specific heat, the more resistant it is to heat, right? So 0.9 so the block of aluminum, it will take the heat, right? But it's a lot more resistant. So it won't go up in temperature as much as a block of iron, right? That block of iron has 0.46 joules over grams degrees Celsius. And so the specific heat is so small. So any amount of heat applied to it, it will just go up. It will just freely just go up way more than the aluminum. So because of that, the answer is true. Okay. On to the next one. 2, fill in the blank. The reaction above is a blank reaction. And if 3.4 moles of ferric oxide reacts with excess carbon monoxide, something will be released or absorbed, right? So the first one, the reaction above is a blank reaction. So the way we can find out if it's an endothermic or exothermic reaction is by looking at this little guy right here, the enthalpy, right? When the H is outside of the equation, then and it's a negative, that means it's releasing energy, right? You're you're losing it because it's negative and it's outside of the whole chemical equation. So when it's negative, it's releasing. And the term for when the system is losing heat or it's releasing heat, that's an exothermic reaction. So because of that, we can cross out a couple one of these, right? If it's exothermic, then it won't be endothermic. It won't be endothermic right here. It'll be endothermic right here. Yeah. And so now it leaves us with H and I. If oh wait, hold on. I made something wrong here. So apparently this is supposed to oopsie daisy. This isn't supposed to say ENT. This is supposed to be exothermic. Yeah, it's a little typo here. Okay. Yeah, cool. So yeah, because we don't want endothermic, right? Let's just say that yeah, we don't want the F or G. All right, so now moving on to the second one. And if 3.4 moles of ferric oxide reacts with excess carbon monoxide, something will be released. Or yeah, it could be released. So the way find out how much energy will be released with 3.4 moles is to look at this equation, right? This equation right here, right? This equation says that when 1 mole, right, there's an invisible 1 right there. When 1 mole of ferric oxide, when 1 mole of ferric oxide is used, right, then then 26.3 kilojoules will be released. That's a rate, right? We need to keep that, we need to write that down. So when 1 mole of ferric oxide, Fe 203 is used, then 26.3 kilojoules. Because right, it's a ratio. It's all proportional. Just the same thing how like you need 1 mole for 1 mole of ferric oxide for 3 moles of carbon monoxide. Same thing, right? So for like in stoichiometry. In this case, 1 mole of ferric oxide will release 26.3. And so what we can just do here is that we have here what we're given, right? 3.4. Oh, why is this like random looking thing here? All right. All right, cool. So 3.4. When 3.4 moles of ferric oxide, goodness, E2O3. All right, this is our given. We need to set up this table. And then all of a sudden, we can just plug this in right here. So what goes on the bottom has to cancel out, right? So 1 mole of ferric oxide. And then what we want, right? What we want over what we have. So we want to have kilojoules. And then the kilojoules is 26.3. So we just put this right there. You punch this into your calculator, right? And you're gonna get 89.4 kJ. And so you look over here, and so you'll see that H doesn't make sense because that's not 89.4. And so now left with I and J, right? So I and J both say exothermic and they both have 89.4. The difference is that it's released or absorbed, right? Since it's exothermic, it's going to be releasing energy. This is why it's going to be I. All right, you're not absorbing it. All right, last one, number 3. If 435.4 grams of block of an unknown composition is heated to 18 degrees Celsius, the block is immediately dropped into a container holding 150 grams of water at 32 degrees Celsius. Once thermal equilibrium has been established, the temperature of the water and the block is measured to 30 degrees Celsius. What is the block made out of? Okay, so two things right here, right? Let's just break it down because I like to break things down. This is a whole lot of words. So a block of an unknown composition, right? It's a block of unknown composition. It's being heated. Oh, oops. How do there's a block, right? Block of unknown composition. It's being heated, right? To 18 degrees Celsius, right here. And then all of a sudden it's dropped into the water. All right, this is 18. And then it's going to be dropped into water at 32 degrees Celsius. Right? So the water is warmer than the block of the composition. So the block of unknown composition is colder. So once thermal equilibrium has been established, like when the cold thing is dropped into the the hotter water, then it's gonna come out to an equal temperature, and that temperature is gonna be 30 degrees Celsius. What is the block made out of, right? So this is a classic Q equals Q. Q system equals Q surroundings, right? And this Q system equals Q surroundings. One of them is going to be negative. Either the system or surroundings doesn't matter particularly. But in this case, since the water is hotter, right? It's at 32 degrees Celsius, and then the block of whatever of composition is being dropped into it. The the water is going to go down to 30 degrees Celsius, right? So it's going to lose heat. So because it's going to lose, we're going to put a negative on the surroundings. And so now we can actually go to solve this equation, right? What element is this block made out of? So what we need to find is the system. This system is the what we're trying to look at. It's the chemical reaction, right? It's the thing that we dropped into it. So the system is the block of unknown composition. So we need to find what Q system is. So in order to find what Q system is, we need to expand out Q surroundings. And just like Q equals MC delta T, we just put QM surrounding times C surroundings times delta T surroundings, right? The mass of the surroundings is the water, right? This water is at 150 grams. The specific heat of the water is going to be where is it? Yeah, right here. 4.18. Because we're still in liquid phase. And then the temperature, the change in temperature. The change in temperature is always temperature final minus temperature of initial. So the final is going to be 30, right? The initial was 32. 30 minus 32 will be negative 2. Let's give it to the change. Equals Q system. Oh, sus. Okay. Anyways, Q system, if you multiply all this out, you're going to get 1,254. Okay, so now you just found your Q system, right? Your Q system is 1,254. And the question asks, right, what element is the block made out of? And what element, so you need to find out like what element it is. And luckily there's a table right here, right? Of elements and specific heat. Specific heat is a C, right? Of a C value. Right. And there's also the list of elements. So when we see that you can find the element based off of a C off of the specific heat value, right? That means we only need to find the C. And look, we have the Q, we have the mass, right? And the mass is 435.4. And we also have the temperature differences. So let's plug that all in, right? Q system is 21254, right? Still using the Q equals MC delta T. Our mass, there you go. Our mass is 435.4 grams. 435.4. Our C, we don't know that because that's what we need to find. That's how we're going to get our element. And then the temperature change, the delta T. We see that the final temperature, the final temperature is 30 degrees. And we also see that the initial temperature is 18 degrees. So final minus initial, 30 minus 18, we're gonna get 12. So it's gonna be our temperature change. And then our C, when you plug all this in, divide both sides, right? C is gonna be 0.24. So great, we just found our C. Now we can go back up to this table, right? Because this table has what we need, it's a key. We look over here, right? We look at what value has 0.24 and then what element does it match it with? So we look further into it, right? And we see 0.24 is right here. This matches with silver. And so the unknown composition is silver. So yeah, that's cycle 5 quiz. Happy studying.